several chemistry and material science challenges. This is an electrolyzer. You input water and energy, and you get hydrogen and oxygen out. And if you run that cell in reverse, in a generic sense, you put hydrogen and oxygen in, you get water out and energy. So it's really a way to store energy. It's an electrochemical cell, like a battery, but instead of all the electrolytes self-contained, you have inputs and outputs of hydrogen, oxygen, and water, respectively. Some of the common themes there are there's electrical energy exposure. So you need a polymer that can withstand exposure to electrical energy or potentials or current. You have chemical exposure, acids, bases, water. Water is a universal solvent, so it's actually a fairly demanding solvent, especially at high temperatures. Then you have hydrogen and oxygen gases. You have various intermediate species, hydroxyls, proton, and then also potentially decomposition products of the PEM, the catalyst, and the source gases. So you could have some small amounts of H2S or HF in the mix as well. In addition, there's thermal stresses and elevated temperature, so heating, cooling, thermal cycling, gas exposure. So depending on the solubility of the gas in the polymer, you could have swelling or possible reaction. And then worse yet, it's under high pressure, so you could have leakage. If you leak hydrogen, obviously it's a safety hazard. And then finally, the mechanical stresses, thermal cycling, gas, hydrostatic pressure, creep resistance. All of these things are combined in material performance requirements for suitability for these applications. So the ideal material you would want is chemically resistant, mechanically and thermally robust with scalable manufacturing so that you can make it in the large quantities that are required for proliferation of hydrogen technology. Fuel cell and electrolyzers engineering challenges. Again, there's an electrochemical cell, but these cells are stacked tens or hundreds together in commercial equipment. So this is a commercial electrolyzer. What you can see is you need very high quantities of components. So you need scalable manufacturing for thousands or tens of thousands of units. And the need is really high reliability, no leaks, and a long lifetime, just like you would expect for other energy sources. So the engineering reliability is dependent on the material in many cases. And so in order to address that, you need to define and then address the potential deficiencies in the materials to get to a good solution at the end. So this is a qualitative assessment of critical to quality requirements: chemical resistance, use temperature, mechanical properties, electrical creep, many of the topics I mentioned earlier. So we want broad chemical resistance. We want stability to 80 to 90 C or higher, depending on the operation temperature of the fuel cell or the electrolyzer. You want mechanical properties to have long-term maintenance, so you don't have creep under long-term loads or failure in that sense. You want an electrically insulative material typically, and you want it stable so that you don't have a change in insulation and get a short. Also, these things are usually bolted together or under high loads, so you want to have a good creep resistance. And you want it to be scalable to tens of thousands of parts potentially. And then, of course, for safety, no leakage. So current materials, PPS, PPA, PEEK, there are a few others that are in the mix too. But in general, many of them have the manufacturability part down. But in the other areas, there's some deficiencies in one or more of the other critical aspects. So it really leaves open an opportunity to develop a better material to service these applications. Valve seats also have similar requirements, but there's more focus on creep, and electrical tends to be less critical. But again, there's some common themes there, a little different in the temperature ranges.